particle, it is a fact. A particle really does take all paths one can possibly imagine, whether they sound reasonable or not, as long as one does not look. Particles move and behave like nothing you've ever seen or experienced in your daily life. You probably got a glimpse of that while touring the inner workings of an atom, seeing that electrons and everything are not just spherical lumps of matter. Now we are approaching an even deeper truth: quantum fields do strange things to particles. Belonging to a quantum field means that particles really do split into many images of themselves, all the time. And the paths taken by all these images fill in every spot there is in space and time, with you having only a chance, a probability really, of finding a particle at one particular time and place, whenever you fancy trying to detect one. Worse still, before a particle of matter or light is detected, its countless images themselves can split up and become something else before turning back into the particle it was in the first place. Just as light can become an electron and electrons can become light, all the particles in our universe can change into something else when we are not looking. Quantum particles are sneaky little fellows. Whatever can happen happens, when nature is left unchecked. And if you do not take my word for it, see for yourself. Something is happening to the endless night of space in which you are floating. A white, doorless cube of a room is beginning to materialize around you, and you soon find yourself inside the room, the walls of which are all covered with extremely tiny, perfectly white detectors. Millions of them. Right in front of you, in the middle of this doorless room, a vertical metal post as wide as your hand runs from floor to ceiling. The only other thing in the room is a yellow machine that looks a bit like one of those mechanical devices that throw tennis balls. This queer little robot almost seems to be staring at you through the end of its throwing tube. Apparently programmed to be polite, it says hello. It doesn't have a mouth or eyes or ears or anything. Yet it talks, with a rather rusty voice. "Hi," you reply, just in case, and start to ask a question. The machine cuts you off, explaining that it is filled with buzzing particles that it will now throw, one by one, to the other side of the room. If you wonder whether they are particles of light or of matter, the answer is that it might be either, since for what you are about to witness, matter and light would fundamentally behave the same. Apparently unable to wait, the robot immediately starts a countdown. 3, 2, 1. The tube emits a particle and an instant later a bell sounds on the other side of the room. You have the curious sense that the robot is rather pleased with itself. You lean ever so slightly to one side and see that one of the wall detectors has turned black, behind the metal post. First question, how did the particle get there? Asks the robot. Unfazed by its blank professorial tone, you move to stand in front of the ball thrower. A straight line links the point at which its delivery tube fired the particle to the blackened detector. The straight line of that apparent trajectory almost touches the metal post, but not quite. That's the path, you announce, raising a finger to point in the only possible direction the particle could have taken. Incorrect, the robot responds simply. I beg your pardon, you say, surprised. Your answer is incorrect, whatever direction you are pointing at, states the robot, making you reconsider its supposedly programmed politeness. But there's only one possible path. I'm looking at it now. If you rely on your senses and on your intuition, the machine continues, then you will continue to answer incorrectly. Every human does so when first entering this room. The rules obeyed by quantum particles are not the same as the ones that rule your everyday life. Your senses and intuition are of no use with particles. Forget about them. However rude you may feel its attitude to be, the robot is perfectly correct. For despite its rather humble appearance, it fulfills the function in this book of being the most advanced computer in the world, and just as computers are often a scientist's best friend in real life, helping them to visualize their theories, our robot supercomputer will come in useful throughout the rest of this book. It can simulate anything that obeys the laws of nature as they are known by mankind. The white room you're in, for instance, is a creation of the computer. But everything that happens within the room obeys the known laws of nature. Now, it may seem that the particle or robot flew perfectly straight, but particles belong to the world of the very small, and are therefore beyond the realms of common sense. The computer said you were wrong because what just happened had nothing to do with what your eyes can detect, or how smart you are. The computer is talking about nature, and nature is both intractable and clear on this point. Quantum particles do not behave like tennis balls, but like the quantum particles they are. To get from one place to another, they take all the possible paths in space and time as long as these paths link their starting point to their end point. The particle the robot shot literally went everywhere. Simultaneously. To the left and to the right of the post. And through it. And outside the room. And into the future and back until the moment when it hit a detector on the wall. Now don't worry, you do not necessarily have to understand this. It actually doesn't matter whether you understand it or not, it just is the way nature works. Particles that no one looks at do travel through all possible paths space-time can offer. The metal post in the middle of the room changes nothing. In fact, it was only there to make the point visually. Take it away and the particle would still travel to the left of where it was and to its right. The detectors on the walls, on the other hand, did make a difference. Hitting one made the particle eventually show up somewhere. Next to you, the yellow particle-throwing robot begins to shake and heat up. You wonder whether it might be about to break down, but anticipating your question, it suddenly begins to speak again. Everything is in order. I am slowing time down. It takes some energy. The next time you blink, I will throw another particle. You will see what the room would look like if you could witness all the paths a particle travels in order to get from the delivery tube to the wall. Without thinking about it, you inadvertently blink, and the robot does indeed start another countdown. The flow of time also begins to slow. 3, 2, 1. The particle leaves the robot in extremely slow motion. At first, it kind of looks like a fuzzy cloud. Moving so as to stand right behind the delivery tube, you then see it split into a seemingly infinite number of ghost images of itself, a wave really, a ripple propagating through the background field it belongs to, traveling in all directions in space and time, including to the right and left of the pole, and through it, and through the room's walls. Splitting into as many possibilities as your mind can imagine, before suddenly focusing back into one spot on the other side of the room, triggering another detector. A bell sounds, the detector blackens and time recovers its normal rate of flow. What you've just seen, courtesy of the computer simulation of a white room, is what scientists believe happens to particles when no one looks at them. When one looks, the whole set of rules changes. When radars keep track of a plane throughout its flight, the plane cannot be at any other position than the one it is detected to be at. Similarly, when one tries to detect a particle, as the detector on the wall did, then the particle isn't everywhere anymore, but somewhere. Contrary to a plane with people inside, however, when no one looks, a particle really is everywhere. On the surface, that might sound like the tree that crashes in a forest. With no one to hear it, did it make a noise? And while we're at it, did it really fall? But we are not talking about philosophy here, we are talking about nature, about how the particles we are surrounded by, and made of, behave. Now why should particles in nature care if a human is watching them or not? Well, many scientists have pondered just that question. And that led some of them to some crazy answers that we'll meet later on, in part 6. For now it is enough to say that what you have just witnessed has been shown to be true by countless experiments. Particles are everywhere, and then they aren't anymore. In the robot's simulation, the detectors themselves forced the particles he threw to hit the wall of the room somewhere. If you are confused, you are right to be, says the robot. I have shown you that the very act of probing reality changes its nature. Say that again, you ask, frowning. Reality changes when you look at it, repeats the robot in a flat tone. And you are right to be confused about it. The very small quantum world, it seems, is a mixture of possibilities. The quantum fields to which all particles belong are the sum of these possibilities, and, somehow, one possibility is chosen out of all the existing ones just by seeing it, just by the very act of detecting it, whenever one tries to probe a particle's nature. Nobody knows why or how this happens, but the result is they're all the same. Multitude becomes singleness when you interact with the quantum world. Just as, from someone else's point of view, all the thoughts you may or may not have at some point in your life on a given subject suddenly become reduced to one as someone hears you speak it out loud. That's what the detectors at the back of the white room did. They forced the particle the robot fired to end up somewhere rather than keep being everywhere, dispossessing it of its ubiquitous nature. As the possible consequences of this begin to dawn on you, you get goosebumps, even though you are still just a shadow. Could this mean that with the right detection equipment, you might be able to make reality your own? Just by trying to detect them, could you make particles matter itself move this way rather than that, molding the whole universe just as you please? Witten said that the universe wasn't made for your convenience, but perhaps he was wrong. Before you start bragging about it, I'm very sorry to say that Witten was right after all, and that your newfound power is a mirage. You cannot mold the universe, because of all the quantum possibilities the quantum world is made of, it is impossible to predict which one will become real after a glance. This is part of the magic of the fields that make up the universe. The quantum world turns what we thought were certainties into possibilities, or probabilities, for us to probe with experiments, the outcome of which no one can guess with total confidence. Just like flipping a coin or rolling a dice. Scientists have thought that this uncertainty was linked to something missing in their knowledge, but it was proven that it is not thanks to a celebrated theorem published in 1964 by Northern Irish physicist John Stuart Bell. Bell's theorem allowed French physicist Alain Aspect to experimentally show that the existence of possibilities rather than certainties is a property of the very small we'll just have to accept. All right. But what does all this have to do with the vacuum you were supposed to probe? Well, that is what you are now about to find out. The detector-filled white room vanishes, along with the metal post that was in the middle of it and the yellow robot, which didn't even bother to say goodbye. You are back in the middle of what seems to be the cosmic night, alone, surrounded by nothingness. You shrink to your mini-you size, and begin to watch the stirrings of something. It is as if a particle just appeared right in front of you, before vanishing in a puff of light. There was nothing around, and then there was something, and now there isn't anything anymore. Strange. And it now happens again. And again. And countless other times, everywhere. What you are witnessing is the apparently spontaneous creation of particles out of nothing. And before they, for some reason, disappear, these particles travel all the possible paths their quantum freedom allows them to take. You can accept the last part of that statement. You saw in the white room that is how unchecked quantum particles behave. But how can they just pop out of nothing? Well, it is not nothing that surrounds them. There are quantum fields around. To appear, particles have to borrow some energy from the quantum fields. And since those fields fill in every place in space and time, particles can literally appear anywhere and anytime. That is the reason why there is no such thing as true emptiness anywhere in the universe. You stare further into the darkness and suddenly, as if a filter had been removed from your eyes, the whole truth of it appears to you at once. Particles. Fusing. Everywhere. filling everything, shooting through a boiling background of fluctuating loops, virtual particles all moving and interacting with each other, appearing and disappearing in puffs of light or energy. An extraordinary firework display occurring everywhere, leaving no spot empty. Pretty much the exact opposite of what you probably once thought was the nothing that filled the vast emptiness of outer space. And this is what scientists call the vacuum. This is what is left when everything is taken out, quantum fields at their lowest possible energy level, with virtual particles spontaneously popping out of them only to move everywhere, before being swallowed back into oblivion. I will say it once more, there is no such thing as emptiness in this universe of ours. In a place from which everything has been taken, you might reasonably have expected nothing to be left. But the fact is that, just as you can't take away space and time from any place, you can't take away the vacuum of the quantum field either. But if the vacuum is not truly empty, if the vacuum of a quantum field is defined by all the particles that can pop out of it, then a rather legitimate question comes to mind: is a vacuum the same everywhere, or can the nature of it change from one place to another? To use its proper plural, are there many vacua? In 1948, Dutch physicist Hendrik Casimir forecast that for a vacuum defined as above, were all this to be a real fact of our universe rather than just a theoretical fantasy, then not only should there indeed be different vacua around, they would also have a very concrete effect on our world. An effect that could be detected. Imagine a wall, mounted on multidirectional wheels, separating a room filled with air from another room filled with water. You might expect to see the wall move, gently pushed sideways on its wheels by the water, in the direction of the air-filled room. Now imagine two tiny parallel metal plates facing one another. If left alone, just like the wall separating the water-filled and the air-filled rooms, they should move, they should be repelled or attracted towards one another, because of the difference between the vacuum they delimit and the vacuum that lies away from them both. Why? For the simple reason that there is more room outside the plates than in between them. Because of this, the virtual particles that pop out of nowhere in between the plates are different from those that appear outside, making the vacua different. As a result, the plates should move, and it just so happens that they do, as was confirmed experimentally by U.S. physicist Steve Lamoreux and his colleagues in 1997. This phenomenon is known as the Casimir effect. The Casimir effect confirms that emptiness doesn't exist, and goes further still, showing that different types of vacua occur and can give rise to a force, the force of the vacuum. 38. Incidentally, you might notice that you've also just found the solution to a very, very deep puzzle. As you've known for some time now, all the particles in our universe are but expressions of quantum fields. They are like waves at sea. They are like balls thrown in the air. They are both, particles and waves, born out of and propagating through the quantum field they belong to. Now, when exploring the very small, do you remember noticing that all the fundamental particles you encountered were always the same? That any two electrons were always exactly identical? 39. How could that be? In your daily life, such perfection simply does not exist. Whatever you do, whatever you look at or build or think, there are no two exactly, perfectly identical objects. Or people. Or birds. Or thoughts. Ever. Even if they look similar, they are not identical. So how come all electrons and other fundamental particles are always absolutely and perfectly identical to any other one of their own kind? The answer is that all the elementary particles, throughout the universe, blossom out of the same background entities that might swallow them back up again at any time, the vacuum of a quantum field. The invisible background seas that fill in our entire universe. All the electrons are identical expressions of the electromagnetic field, they all pop out of its vacuum and propagate through it. And so do all the photons. Every time an electron becomes real, it is awoken out of its ghostly lethargy by a kick in the surrounding electromagnetic field vacuum. Every time a gluon appears, it comes from some energy given or taken from the vacuum of the strong interaction field. Every time radioactive decay occurs, the weak field's vacuum is involved and fires off its elementary neutrinos. And the more energetic the vacuum is, the more elementary particles can pop out of it. Alright, we're on a roll, so let's continue. It seems that all the fields behave the same, that they all obey the same rules. Now, what about gravity? Anywhere gravity acts, a gravitational field is actually in effect too, although that field is different, at least for now, because no one knows how it could be a quantum field. As you will see later on, no one knows how to make particles pop out of a gravitational field vacuum without creating catastrophic problems. But if it were possible, then gravity would involve particles that, as with all the other fields, would indeed pop out of the gravitational field to carry its force. These particles are called gravitons. They haven't been detected yet, and curves of space-time are still the best way to explain gravity's action. But even without them, and even if it perhaps isn't quantum in nature, gravity is nonetheless a field. And that makes the total number of fields used by mankind to describe everything we know so far to be 4. But why 4? Why should there be 4 fundamental fields? Why not 5 or 10 or 42 or 17,092,008 to explain the way nature behaves? And how about their respective vacua? Are they just cohabitating everywhere without noticing each other's presence? Sounds odd, doesn't it? Wouldn't life be simpler if there were just one field? It would. And simplicity is something theoretical physicists are always very keen to find. It even drives their imagination, and that is why they have tried to merge the 4 known fields above into just one. One field to rule them all, you might say. Easier said than done, though. Each field's elementary particles aren't even the same. And one of them doesn't even have any particles that have been detected. And exciting one field gives different outcomes to exciting another. And they don't involve the same charges. And they don't have the same properties at all. In fact, electromagnetism is long-range in its effects and can be either attractive or repulsive, while gravity is only attractive and the strong interaction very short-range, and yet, to create an alloy out of 2 different materials, you need to heat them up. Heat them to a high enough temperature and they melt into something entirely new, a new material that unites them both. For fields to merge, the same idea could work. But an inconceivable amount of energy would be needed. A temperature of around 1,000,000 billion degrees is required to turn the electromagnetic and the weak nuclear fields into one. 1,000,000 billion degrees, that's definitely out of bounds of the nature we know today. But it may not always have been the case. In fact, such an enormous amount of energy did happen to be available everywhere a very long time ago, when the universe was younger and smaller. And trying to work out, on paper, how nature behaved back then, Salam, Glashow and Weinberg managed to merge the electromagnetic field with the weak field, thus discovering the electroweak field. They found out that under extreme conditions, a single field contained the 2 fields that today separately rule magnets and radioactivity. The next step is to unite this new field with the 3rd known quantum field, the strong interaction one, the one that rules how quarks and gluons interact within atomic nuclei. In doing so, we might create something that has been pompously dubbed the Grand Unified Theory. To do that, an even greater energy is needed. How much more? A dizzying amount. So much that adding 1 billion degrees or 2 doesn't make much difference. Now, how do we know if all this is real? How do we know that Salam, Glashow and Weinberg got it right? And apart from the feeling that one makes more sense than 3 or 4, how do we know that there really is a grand unified theory out there waiting to be found? Because in uniting the fields with one another to create a new one, physicists predicted that such a new field should have its own fundamental particles and force carriers. To test this, they have built particle accelerators in which already existing particles are smashed against one another. Within such accelerators, not only are the particles broken apart, showing us what they are made of, the tremendous energy around the collision also excites whatever field lies dormant in this universe of ours. The maximum energy reached around the impact in such collisions, as of 2015, corresponds to around 100 million billion degrees. That might sound like a lot of energy, but it's worth remembering that we're talking about a particle accelerator here. It doesn't accelerate cows or planets, but impossibly tiny particles. In actual terms, the energy produced by these minuscule collisions would barely power the flight of a mosquito. Locally, however, the energy released is enormous. And just as Salam, Glashow and Weinberg predicted, entirely new particles were brought into existence, particles that only make sense when considered from an electroweak perspective. I don't know about you, but such achievements never cease to amaze me. Now, what about gravity's role in all this? To turn the four fields into one, gravity has to play a role, so why leave it out? Answering that question will be the goal of the whole of Part 7. But don't be impatient, because with what you've seen so far, you've learned almost everything there is to know about the matter you are made of, with one big exception, your mass. Put like that, you may wonder how come you haven't heard about it before. It seems to be quite an important question, doesn't it? So, where does mass come from? Stars forge large atomic nuclei in their hearts, as you know, out of small ones. So do stars also create mass? No, they don't. They actually do the opposite. By expelling the gluons made redundant during the fusion process, the neutrons and protons lose some of their energy, and hence mass, as dictated by Einstein's E equals mc40. This is the origin of the energy that makes stars shine. You've seen this happen. But this also tells you something else. If atomic nuclei lose mass by ejecting their gluons, it means that the gluons were that mass. It tells you that part of the mass of the atoms comes from the very existence of the virtual gluon soups that keep the quarks jailed. In fact, when scientists looked at this carefully, they realized that this gluon soup energy present within all neutrons and protons of our universe accounts not just for some, but for a huge chunk of the mass of the matter we know. A huge chunk. But not the whole of it. It doesn't tell us, for instance, why quarks and electrons are massive. Or how they became massive, rather, for it so happens that they once were massless. Salam, Glashow and Weinberg showed that a long time ago, as our extremely young universe expanded and cooled down, the electroweak field branched into the electromagnetic and weak fields. But what I didn't tell you before is that for this to have happened, another field had to appear. Another quantum field, with its own force carriers and all. These force carriers can't be carrying any of the forces you've already met, and there isn't any other force to account for. So what do? Well, they gave a mass to some particles and left the others massless. The photons and the gluons, for instance, did not feel its presence and they still do not feel it. They can travel through its field without noticing it. So they stayed massless and they still travel at the speed of light today. But quarks and electrons and neutrinos did notice its presence and became massive. Because of that, they can't reach the speed of light anymore. Again, how do we know this to be true? How do we know a mysterious field is responsible for the masses of these particles? Well, like all fields, this new field should have its own fundamental particles. As expected, however, they are not easy to see or detect. According to calculations, for this field to be awoken and give birth to its fundamental particles, a tremendous amount of energy is needed, even more than for the electroweak field itself. Still, in 2012, as amazing as it sounds, scientists managed to do exactly that at the LHC, the most powerful particle accelerator of the European Centre for Nuclear Research, near Geneva, in Switzerland. 41. They detected a fundamental particle that belongs to this field. It was the missing piece of the puzzle. The origins of all the known mass of our universe, be it due to gluons or not, was then known. It indeed confirmed that physicists had been on the right path all along. The media called this detected particle the Higgs particle, and the field it was extracted from is known as the Higgs field or the Higgs-Englert-Brout field. British theoretical physicist Peter Higgs and Belgian theoretical physicist François Englert jointly received the 2013 Nobel Prize for this discovery. In short, they had discovered how some of the mass came into being 13.8 billion years ago, as our universe cooled down. A very impressive feat for them and for mankind. Because this discovery made the headlines, it may nonetheless be noteworthy to underline again that the Higgs field is not responsible for the mass of everything that we are made of. Just some. Most of the mass of the neutrons and protons comes, as we said above, from the force that confines the quarks within their boundaries, from the quark-gluon soup that lies in there. If the Higgs field was suddenly turned off, then quarks would become massless and we'd die. But the mass of the proton and neutron would barely change. Now that the strong field's role in our being massive is vindicated, now that you know where all the mass of all the matter we know of comes from, think back to all those particles that you saw popping out of the vacuum earlier on in this chapter. You saw them. But you shouldn't have. Nature doesn't let particles appear on their own like that without paying a price. This price, as you are now about to see, is the existence of a new type of matter named antimatter. 3. Antimatter. For almost all of Earth's history, its surface was mostly unknown to human beings. Today we have easy access to satellite images of our entire planet, but, as recently as a few centuries ago, when only a few patches of European, American and Asian soil had been charted by the people who lived there, no comprehensive image of the world prevailed. Intrepid explorers from many civilizations therefore had to leave the safety of their shores and sail through gales and storms to figure out what, if anything, lay beyond their homelands. One after the other, they found faraway land masses upon which no fellow man or woman had ever stepped. They found other civilizations too. Small pieces of rock surrounded by water became called islands. Large ones, continents. Each such discovery increased the realm of mankind and, at the same time, tended towards making our ancestors grasp a very simple fact: we all live on the surface of an incredibly rich but rather small ball that drifts through an immense universe. Decades went by. Through a mix of violence, greed and curiosity, Earth became better known. The unknown gradually changed from being somewhere beyond the horizon to everywhere above our heads. Space became the new mystery everyone could wonder about, just by looking up. But the distances out there are mind-bending. As this book is being written, human-made satellites have been sent several 100 million kilometers away from Earth to try to figure out the origins of the water, and maybe the building blocks of life itself, on our planet. Exploration is not just about sending humans on perilous adventures anymore. Robots do that for us. But as excitement about interplanetary travel is on the rise again, is it possible, in the early 21st century, to stay on Earth and still be an explorer? Of course it is. One could aim for the bottom of the oceans, an environment so hostile to our technology that fewer people have made the plunge down there than have set foot on the moon. Or one could have a different approach altogether, and do science. Although science might not be as glamorous as sailing a caravel or piloting a rocket ship, it can carry you anywhere. From the bottom of the seas to the edge of our visible universe. And beyond. As you've probably noticed while reading this book, your mind can take you to places forbidden to your body, and to places where no one has ever been before. While delving deep into the nature of space and time, or the quantum behavior of particles and light, no two readers of this book will have made exactly the same journey, none will have pictured the exact same things. In creating galaxies and virtual particles of light in your mind, you entered the world of theoretical research, a world without limit. No one ever knows in advance in which direction an undiscovered island or a continent may be found. And many an explorer must fail in order to pave the way for a great discovery. Luck indeed happens, but it isn't reliable. Building upon past discoveries, however, is the same is true of science, and the discovery of antimatter follows this ancient, pioneering path. One genius of a man opened everyone else's eyes to the following amazing fact: the matter we are made of, the matter that makes up the planets, the stars, and the galaxies themselves, is but half the matter there is, and he did not figure this out by sheer luck. He was building upon what had been done before him. Explicitly, on Einstein's work on how things move when they move very quickly, and on the curious ways quantum particles behave. That man was Paul Dirac. He created the idea of a quantum field and consequently discovered antimatter. Dirac was a British scientist who, between 1932 and 1969, held the Lucasian Chair of Mathematics at Cambridge University, one of the most prestigious scientific chairs in the world. Isaac Newton sat on it between 1669 and 1702, and so did Stephen Hawking, between 1979 and 2009. So what is this antimatter? You already know what E equals mc means, that mass can be converted into energy, and energy into mass, with quite a high exchange rate. And as you have just seen in the previous chapter, that energy can be borrowed for a short amount of time from the vacuum, from the fields, to create particles. Now back to your mini-you. You are still in an empty universe, surrounded by a vacuum, specifically a vacuum of the electromagnetic field. Right in front of you, an electron pops out of it. Why? Because it can. So you see an electron appear. Pop. Just like that. A moment ago, there was nothing but the vacuum. Now there is an electron, and the electron has a mass. The very fact of it having appeared means that some dormant energy has been transformed into that mass. That's E equals mc in action. That's easy. But the electron also has an electric charge. Which rather begs the question, where does that electric charge come from? Mass comes from energy, and mass and energy are equivalent, so the appearance of mass out of borrowed energy is a balancing process. It's just a change of energy from one form to another. But the electric charge is a different problem altogether. After the electron appears, a negative electric charge also appears. Before, there was none. After, there is one. And that, surely, is not acceptable. As I mentioned at the end of the previous chapter, you can't create something out of nothing without having to pay a price for it. That never happens in real life, I can hear you sigh. And for once it is the same in the quantum world. So, what do we do with this charge? Do we just turn a blind eye to it? We can't do that, because there is far too much of it. Every electron in the universe carries a charge, and many other fundamental particles do too. So where does the charge come from? Well, the easiest answer often being the right one, here it is: an electron never appears alone. It must appear alongside a particle that is identical to it, except for its charge, which is opposite. Such a particle is called an anti-electron. It was introduced so that the charges of all the electron, anti-electron pairs that have ever been created adds up to zero. No need to invoke E equals mc anymore, or indeed anything else. Such a phenomenon doesn't violate any laws. The total charge was zero before the electron and anti-electron appeared, it still is zero afterwards. That is what Paul Dirac, somehow, brilliantly figured out. What's the big deal? You'd be forgiven for wondering. Well, a particle that is exactly similar to an electron, with opposite charge, was not known to exist at the time. No one had ever seen an anti-electron. Today, we detect them everywhere. The process by which an electron and its anti-self appear out of nothing is called a particle-antiparticle pair creation, and the opposite process also exists. When an electron meets an anti-electron, they annihilate, they disappear, puff. Gone, their mass transformed back into energy, into light, in an instant. Electrons and their anti-selves are created out of the electromagnetic field, and they melt back into it when they annihilate. Now, since electrons exist on their own, and since they were all created out of the electromagnetic field during an electron-anti-electron pair creation, it follows that anti-electrons should also exist on their own. And indeed they do. But they are not to be found everywhere. In 1928, Dirac had called the anti-electron a hole in the sea being what we now call the electromagnetic quantum field, because it corresponded to some charge that was missing. His hole, the anti-electron, was discovered experimentally 5 years later in 1933, and Dirac received the Nobel Prize in Physics that year for his extraordinary insight. His theory of fields encompasses all those very fields you've been seeing everywhere since you started to explore the world of the very small and discovered antimatter. It was U.S. physicist Carl D. Anderson who actually detected Dirac's anti-electrons for the very first time. Instead of calling them anti-electrons, however, Anderson gave them a new name, positrons, a name that is still in use today. Anderson got the Nobel Prize for his detective work 3 years later, in 1936. With this, antimatter was born. I said earlier that half of all matter was antimatter. But if it's only anti-electrons, then it's not half of everything. What about the anti-quarks and anti-light and anti-gluons? Well, what is true for the electron is true for all particles. They all have their anti-selves. Anti-quarks exist, and so do antineutrinos and antiphotons. But some particles, ones that do not carry a charge, can play both sides and be their own antiparticles. Light is a good example, because photons and antiphotons carry no charge, they are identical. So why don't we see all the other antiparticles around us, everywhere we look? The answer is that they are there, around us, around you, but not in large quantities, because whenever one appears, it only lives for a very, very short time. Remember, any antiparticle that bumps into its particle counterpart immediately annihilates with it, only to disappear into a puff of energy and light, according to E equals mc. Somewhere else in the universe, however, a whole world could be built out of antimatter. An anti-world, if you like. No one knows if such anti-worlds exist, but if they do, and if you happen to end up facing someone like you in outer space someday, don't shake hands. You and your anti-you would become a bomb and immediately explode. Violently. Point 43. Still, there is some antimatter around nonetheless. Even inside you, right now. Every time an instance of radioactive decay occurs, some antimatter is created, only to annihilate with its matter counterpart to become a ray of light so powerful that it usually shoots through your body, without you, or anyone, noticing it. Your eyes can't see these rays because, as we discussed earlier, your eyes simply never needed to evolve the capacity to detect them. But what your eyes cannot see, technology can, and some quick-witted engineers have managed to turn that discovery into efficient medical diagnosis and research tools. PETs are an example. They are used in hospitals. PET stands for positron emission tomography. Doctors inject liquid tracers into your body that are themselves radioactive, and which emit a positron when they decay. The positrons then annihilate with electrons in their path, turning into powerful gamma rays that are detected outside your body by the PET machine to reconstruct a 3D image of how your body works. It's quite brilliant. All right. You now know about fields and their vacua. You know about their possible unification. You know about mass and charges and antimatter. And this means you are ready to travel beyond what you've seen in Part 1, to the Big Bang, and beyond still, to the origins of space and time. So I'd take a deep breath, if I were you, before turning the page. 4. The wall beyond the wall. For years, without thinking about it, you probably took for granted, quite unconsciously, the fact that this universe of ours is mostly emptiness and entirely fixed and unchanging. Unlike our ancestors, you might have heard about the Big Bang, but you perhaps never really thought about what that term might actually mean. In fact, in many ways we are all like those fish swimming in the sea. Except, as you now know, that we are not swimming in a sea made of water, but in the many seas that our friend Dirac charted, seas that are called fields, and that fill the entire universe, fields of which we are a mixed and rather complex expression. Thinking about it, you reckon that it kind of makes sense that everything becomes much easier to understand this way: time, mass, speed, distance, all intertwined within these fields. The universe is huge. Unbelievably large volumes stretch between any two stars, galaxies, clusters of galaxies. But there are no voids. There are only fields that allow for distant objects to have an interaction, by exchanging particles, their so-called force carriers, without ever touching each other. Fields link everything to everything. There is something almost reassuring in that thought. And as you are about to rewind the whole history of our universe up to the birth of space and time, you may wonder, over the course of human history, could all those shamans and holy men and tripped-out people who have shouted, cried, sung, written, painted, danced, over the ages, that one is all and all is one have been right? Well, in a far-fetched sense. Maybe. But they certainly did not know why. Our supercomputer of a robot does though, and it has reappeared. Once more the bright yellow tennis ball throwing machine is right in front of you. It still doesn't have a face and looks at you rather blankly with its particle delivery tube, but you now know better than to see it as just a mechanical machine. Feeling strong and buoyed with the confidence of all the knowledge you've gathered so far, you prepare your mind to stretch itself once again, to picture the whole history of our universe. A metallic voice chimes out of the void. Are you ready? It asks. You know it is going to bring you to the origin of space and time, but the robot doesn't leave you the time to answer, and an instant later, you are with him in the sky. Above a house. Your house. The computer has brought you back from wherever you were to above your hometown. And you are now both shooting upwards. You cross the different layers of our planet's atmosphere and reach space again, where you settle above your home world, to face outer space. I am going to have you fly through the best simulation ever made, announces the robot. When programmed, as I am, to obey the laws of nature that have been unraveled so far, even the most powerful supercomputers on Earth struggle to achieve what you are about to see. Then let's go, you exclaim, feeling the excitement of the journey build, itching to go beyond what can be seen and cross all these interleaved layers of paths that pile up around the Earth. You know that if you wanted to reach a star normally, with your body rather than your mind, then you would have to spend some time traveling, and the star would not be as it is now when you reach it. It would have evolved. Just as if you wanted to travel to New York now, it would still take a few hours to get there. The New York you'd reach would be different from the New York that was there when you set off. People and cars and clouds and raindrops, nothing would be in the same place anymore. While traveling to a faraway star in a faraway galaxy, the difference would be even bigger. By the time you reached your destination, the universe would have expanded. The cosmic microwave background, the overall temperature of our universe, would be colder, the surface of last scattering further still. Traveling normally, however fast, you'd never reach the past. So how can the computer simulation propel you into the past, and the very distant past at that? The answer quickly dawns upon you: to find yourself in the universe as its infancy unfolded, to see it happening, you shouldn't move. You should just let time run backwards, and that is exactly what starts to happen. Without moving, you begin a new journey, traveling backwards in time through the history of our universe to reach the Big Bang and beyond, from the point of view of where you are. Showing a sensibility you had not expected of him, the computer's robot avatar even kindly fades away so that his presence doesn't hinder your sight. In a blink, you are 7 million years in the past. The surface of last scattering, the surface delimiting the end of the visible universe as seen from Earth, is already slightly closer, and it is filled with a slightly hotter cosmic microwave background radiation. But 7 million years isn't much compared to the 13.8 billion year history of our universe, and nothing out there in the sky is particularly different from a moment ago. The Earth beneath you, however, is. Down there are no towns or cities, no twinkling street lights. The first humans are just beginning to differ from the great apes. Your distant ancestors are quite hairy, hunting beasts. Humankind has indeed come quite a long way. Another blink and you are 65 million years in the past. The dinosaurs have just been wiped out by a mixture of violent volcanic eruptions and a cataclysmic collision with a 10-kilometer-wide asteroid, leaving only small mammals alive, some of which will one day, after many successive evolutions, become the hairy ancestors you just saw, and then us. Another blink and you are more than 4 billion years ago. The Earth just got hit by the Mars-sized planet that took a chunk off it to create the Moon. The microwave background radiation is definitely starting to be hotter, and the surface of last scattering now really does look closer than before. The whole visible universe, as seen from when you are, is less than 70% of what it will be in 2015. You rewind another couple of billion years. The visible universe is less than half the size you started from. Earth does not yet exist. In its place, stars are dying right in front of you, extraordinary explosions that spread the matter they were made of through outer space. In a few 100 million years' time, this dust and debris will gather into huge clouds, and gravity will drive the formation of at least one new star, the Sun, and its planets. Another blink, and you are 5 billion years before Earth was born, 9.5 billion years before you were born. Your visible universe is less than 25% the size it will be in 2015. The surface of last scattering is much closer to you. In between you and this wall, galaxies are forming around some gigantic black holes, sometimes meeting in collisions of unimaginable magnitude. Another blink and you are 13.7 billion years ago. You are still where Earth will someday be, but the visible universe, the universe that surrounds you, is now less than 0.5% the size of the one you started from. You are within the dark ages of our universe. The dark ages you traveled through in part 1 of this book were cold because, back then, you flew through what they look like as seen from Earth in 2015, after more than 13.7 billion years of expansion. 13.7 billion years ago, however, things were neither cold nor dark. And you are there now. The first stars haven't ignited yet, so none of the matter you can see has been processed through nuclear fusion in star cores. You are therefore surrounded by the smallest atoms that can be, hydrogen, mostly, and helium. And the radiation that glows throughout the cosmic microwave background radiation is not microwave radiation either. You can see it with your eyes. It is the light that originally filled our universe, a light that shines brightly everywhere, a light that will only become microwave radiation much later, after several billion years of our universe expanding. Another blink and you are 100 million years earlier, 13.8 billion years ago. The surface of last scattering, the surface at the end of the visible universe, is now 1 light minute away from you, meaning that your visible universe is just 1 light minute deep, less than 1/8 of the distance separating Earth and the Sun. The whole universe has been transparent for just 60 seconds. And it is hot. 3,000 degrees Celsius, everywhere. Still in the dark ages, but everything around is so luminous that you wonder if the description really fits. You pause there. In a moment, the computer will start rewinding time some more, albeit at a slower pace, and you will enter a strange, literally invisible place. One further minute into the past and you'll have started what sounds like the ultimate journey. The surface of last scattering is right in front of you. You take a deep breath, ready to cross it, to travel beyond the wall, to reach the unseeable. Time rewinds. And you're through. You've entered a part of our universe's past that will never be seen with light. Indeed, you can't see anything anymore. Light does not propagate here. There's simply too much energy around. But you know what to do. You immediately switch into yogi mode and, to your great surprise, you realize that the universe beyond the surface you've just crossed is big. And old. At least 380,000 years old. Your journey is far from over. You concentrate once more on what is around you, on what is happening now, behind the wall at the end of the visible universe. The surrounding temperature is 5,000 degrees Celsius. All the electrons that will one day bind to loose atomic nuclei to become hydrogen and helium are here on their own. Photons bump into them, exciting them, before being emitted back, only to bump once more into another electron. The electromagnetic field is so filled with energy that all its fundamental particles turn into one another in almost no time. Another blink and you've run tens of thousands of years backwards from the moment the universe became transparent. You are surrounded by a dense broth of particles, a mixture of all the excitations of the quantum fields, their elementary particles and their force carriers. All bumping into each other, none of them managing to travel at all. There is too much energy around. They appear. They collide. They disappear. And as time keeps rewinding, as the universe continues to shrink, as the energy density rises, everything gets more and more violent. Still, you try not to get confused, and focus on your journey backwards in time. You are pure mind, and in yogi mode, traveling through what looks like a very, very realistic simulation. The universe keeps shrinking, its fabric, space-time, bent to prodigious levels. Nothing you know or imagine would stand such crushing and shearing power. For a split second, you wonder why you have not heard more about gravity at this stage, but you have no time to think about that. You have gone back in time some tens of thousands of years more and you are now surrounded by an unimaginable inferno. Your virtual heart starts thumping harder and harder as the temperature and pressure and the effects of gravity on what you see rise to unbelievable levels. You now are 380,000 years before the universe became transparent. Looking through a telescope now on Earth, seeing back over 13.8 billion years, you are 380,000 light-years beyond the wall that marks the limit of the visible universe. Looking at it the other way round, you are about 3 minutes away from what one might call the birth of space and time. As time continues to run backwards, even the atomic cores are breaking down, leaving all the neutron and proton quark jails free to move on their own. The strong nuclear force itself is overwhelmed by the ambient energy. Protons and neutrons, those sturdiest of constructions, even enter a frenetic dance in which, pounded by quark-made force carriers, the protons, bewildered, turn into neutrons, disappearing from the universe. The temperature? 100 billion degrees. Everywhere. But you do not stop. You keep moving. Rewound second after rewound second, all the particles of light that surround you now turn into matter and antimatter pairs. Everywhere. And there seems to be as much of the latter as of the former. How did one end up becoming predominant, then? You wonder, in a semi-trance. Something special must have happened around here, for that equilibrium to have been broken. A mystery that may even be solved this year, or next, as the updated and boosted particle accelerator LHC starts revealing its finds. You wish you could stay here just a little longer to figure it out for yourself and scoop CERN, but you are not in charge here, and you are now cruising through a universe filled with a soup of such formidable energy that everything is shaken to the extreme, gravity bending and crushing, fields excited to levels beyond sanity. It is not the weight of a star that gravity, through the bending of space and time, imposes upon every field around here, but the energy of the whole universe squeezed within a sphere 100 light-years in diameter. 44 such a sphere, centered on today's Earth, would contain no more than 5,000 stars. Back then, it contained the energy to build hundreds of billions of galaxies that each contain hundreds of billions of stars. Not to mention the dust. Still, as much as you would like to look at it all, you keep flying against the stream of time. You now are about a millionth of a second away from your final destination. The temperature has reached 100 million billion degrees. With so much energy around, even the quark jail guards, the gluons themselves, can't keep their prisoners confined. The neutrons break down. The quarks, now free, start to interact with their anti-selves, turning into pure energy. As you look around, you realize that the difference between matter, light and energy is now completely superfluous. Fields that had been separate entities all the way from Earth's time to here, fields that on Earth described everything you could think of, through different forces, are now merging into one another, as expected. The electroweak field is active. As some of the old particles you are used to seeing everywhere disappear, new ones, fundamental entities belonging to the electroweak field, pop out everywhere. The Higgs field vanishes. And with it, the massive Higgs particles that remained hidden to human knowledge for so long. The particles you now see are the Wand-Z bosons we met earlier, the force carriers of the electroweak field. There is so much energy around that these particles, so hard to create on Earth, are everywhere. The universe is now 100 billion degrees hot, and the laws of nature begin to differ noticeably from those you've experienced throughout your life. Quarks and anti-quarks disappear. Gluons are swallowed within the background field. A thousandth of a billionth of a billionth of a billionth of a second after what is nothing less than the presumed origin of space and time, an event we might call the beginning, what will one day become our whole visible universe is now a sphere 10 meters across, and it keeps shrinking. Everything it contains is now heated to a fantastic billion degrees. And as it keeps heating up, all the fields that make up all the matter we are made of unite to become the grand unified field. Only gravity lies outside this unification of the forces. Being so close to the beginning, you start to believe that not much could still happen. In fact, you've just reached what has been called the Big Bang, the moment the energy stored in the grand unified field began to turn into particles. But astonishingly, even though experimental physics has never reached such a place, the computer seems unwilling to stop, if only to show you that the history of the universe does not begin there. Indeed, to your great surprise, as time keeps rewinding, the whole universe's matter and energy suddenly vanish, and contrary to what you might have expected, everything cools down tremendously while all the available energy is turned into yet another field, a field you have not met before, a field filled with its own particles. It is called the inflaton field. It is considered to be responsible for our universe's initial expansion. As crazy as it may sound, everything now suddenly speeds up again, and the whole universe mind-bogglingly collapses in on itself at an unimaginable rate, dragging you in. In less time than it would take light to cross the core of an atom in your kitchen, the whole universe shrinks from about 10 meters in diameter to a size billions of times smaller than a proton. Scientists have called that period the cosmological inflation point 45. You've just been through it backwards. Beyond, there is no more matter, no more anything. All the known fields are gone. The laws of nature bear no resemblance to the ones you've experienced throughout your life, or throughout your journey up to this point. It is somewhere around here that the three forces or fields that will go on to rule all the known matter and antimatter of the universe in the present day, including the matter you are made of, or once, it is believed, merged with gravity. You would like to keep going, to keep rewinding further beyond the Big Bang, all the way through the birth of our universe, but there is something wrong. The notions of space and time you've used until now do not apply anymore. The gravitational bending of space-time is too strong. Quantum effects are too strong. With no time, with no space, with no space-time, you cannot travel anymore. Travel does not actually make any sense in such circumstances. You haven't reached the beginning, and you do not even know how to think of a way to get there. How frustrating. And you suddenly wish you could look at all this from outside, for you've always stayed inside the universe so far. But the very concept of outside doesn't seem to make any sense either. What you've reached here is the surface of another wall, a wall of a different nature from the surface of last scattering that limits what you could see from Earth. This is a wall impenetrable not to light, but to modern knowledge. Beyond lies the realm of quantum gravity, where all the known fields of nature may be united into one, in a quantum way. There, our universe becomes a mystery in which 21st century sciences, beliefs and philosophy are intertwined. In a way, this is where our knowledge stops, and where pure theoretical research takes over. To travel beyond the surface of last scattering, you cannot use light-gathering telescopes, but scientists have built particle accelerators that allowed them to reach the temperatures and pressures they expected to find beyond, and it worked. Scientists figured out new laws, and they managed to crawl back along the flow of time, albeit in an indirect way. As you read these lines, they are even building telescopes to detect not light, but gravitational waves, ripples that propagate through the very fabric of spacetime. Such telescopes might detect signals originating from beyond the surface of last scattering, from some of the distant past that you've just traveled across. But to travel beyond the wall of quantum gravity, also known as the Planck era, is a different proposition altogether. No one is even certain how to think about what lies beyond. Our whole visible universe was so tiny back then that to probe it in your mind, you need a theory of the immensely big turned minuscule, a theory in which the quantum laws, with their quantum jumps and all, are applied to the universe itself. You need gravity and quantum effects. You need quantum gravity and more. And we don't have it. We do not have that working framework. So you cannot go further. In fact, you are not even allowed to infer what lies beyond that Planck wall, neither in space nor in time, because these two notions do not make any sense there. When scientists say that our universe is 13.8 billion years old, they mean that 13.8 billions of years have passed since the space and time you are used to started to make sense, since space-time made sense. And that moment occurred something like 380,000 years beyond the surface of last scattering, 380,000 years before the cosmic microwave background radiation filled outer space. And that moment occurred some millionth of a billionth of a billionth of a billionth of a second before the Big Bang. In the end, scientists can rightly say that such a time has elapsed since the origin of space and time. But it does not mean our universe started there. Nor that it is the only universe there is. Nor that it is the only one to have ever been. You are back in your living room, back on your battered old sofa, and you are struck by a sensation so profound that you grip your sofa's armrest. You've traveled through space and time. You've seen galaxies. You've seen stars. You've seen fields. You've seen how gravity works, how its effect on the shape and fate of spacetime depends on what the universe contains. Yes. You did all that. And now something amazing is starting to happen to you, as if you were on the verge of making a groundbreaking discovery. Thoughts are racing through your mind. You feel like a kid again, a kid who suddenly realizes that the world can be understood, that the world, somehow, up to some point, has been understood, and the computer showed it all to you. You learned from Einstein's general theory of relativity that you could figure out the entire history of the universe, if only you knew what it contained. You now know that the contents of the universe consist of quantum fields that move and evolve and interact, fields that today are 3 but were once 1, a long, long time ago. Those fields are the mothers and fathers of all particles and antiparticles of our universe, and they are the reason why all elementary particles are exactly the same, whether here, inside your body, or in any other galaxy, in the present or in the past. And all this can only mean one thing. It can only mean that, potentially, you've become a god. Yes. A god. You know about gravity. You know what lies inside the universe. Put the two together, and you know everything. The universe's history. Its past. Its present. Its future. You are a god, almost by definition. Your whole face lighting up, you immediately pick up your mobile and dial the number of the only person you can think of right now. Who is this? The voice on the other end of the line sounds suspicious. It's your great auntie. It's me. Oh. Hello, dear. How are you doing? Are you feeling better? Better? I feel amazing, you exclaim. That's nice to hear. Has something happened? I've been traveling and learning about the universe, and... Well, I know it sounds silly, but I can create and evolve a universe like ours just by using my imagination. This must be what it feels like to be a god. Your great auntie pauses. I see, she says. What do you see, you ask, wondering why she so obviously doesn't share your enthusiasm. Nothing. Nothing. It's just that, well, I've heard that one before. You have? People like to play at being gods, don't they? Do you remember my dear friends Katie and Gabby? I don't, no, but listen, what I'm. Let me finish my story, dear. So, Katie and Gabby and I went to the archery field last weekend. Katie and Gabby are quite fond of shooting arrows, you see, and they taught me this, with some quite rudimentary knowledge of how our world works. It seems that knowing how an arrow is shot and where from, you can tell where it will fall. Fascinating, isn't it? Sure, Auntie, that's ballistics, that's Newton's law. Is it? Well, that's good to know. And can you apply that to the whole universe? What? Do you have something to start from, or with? Do you have something to which you could apply your ballistics or whatever laws of nature you've apparently found? Some sort of initial condition, you mean? I don't know. Do you want me to ask Katie and Gabby to give you a call so you can talk about it with them? They're really rather good at this sort of thing. No. No need for that. Okay then. Will you call me back when you've found your initial condition? I will, okay. Thank you for calling me, dearie. You are a sweetie. Bye now. With this, she hangs up. And as you stare blankly at your phone, let me tell you this, as you've probably figured out yourself, she's right. To understand something about the universe, you need two pieces of data. The first one is a law, or a set of laws. The second one is an initial condition. To apply to the universe as a whole the same ideas you've had so far, to know its whole destiny from scratch, then all the laws in the world wouldn't be enough. You'd still need a rock-solid initial condition, a state to which you could apply the laws of evolution. And you just don't have it. And to make it worse, how can you even be sure that the laws of gravity and of quantum fields as you know them even applied at the very beginning of our universe? With a sigh, you sit back in your sofa and grab your mug of coffee with the feeling that some important data is still missing somewhere. 5 lost pasts are everywhere. Space. Time. Space-time. What remains to figure out about them that you have not already seen? Particles. Force carriers. Fields. Gravity. Haven't you experienced all there is to know? And why are you feeling so phased? You open your eyes. To your great surprise, you are not at home anymore, but instead sitting in a cramped seat on a strangely familiar plane. Seat 13A, to be precise. The other passengers are lining up in the corridor, getting ready to disembark. You stare out of the little window, confused, but there is no doubt about it, you really are back inside your time-traveling plane. And it has just landed, in 2415. Finding it hard to think straight, you stand up, follow the other passengers out, and find yourself walking through long, seemingly endless glass-walled corridors overlooking the sea. Why are you back here? A moment ago, you were at home. You had just called your great-auntie after having traveled throughout the known universe. Centered on the Earth, you remember, there is a sphere 13.8 billion light-years in radius which contains all the pasts mankind will ever be able to collect using light. Beyond, another layer of reality existed for 380,000 years. And beyond that? No one knows. As you keep walking through yet more corridors, a bright 2415 sun shining its 8.3-minute-old rays upon the future Earth, an unfathomably deep feeling of loneliness suddenly hits you. What is the point of all this? How can this universe of ours be so big, and we so small within it? Are we forever doomed to be lost in space and time? And tortured by our own awareness of that fact? Or are we humans at the beginning of a long technological journey that will someday bring distant worlds closer? Is that what is happening here? Are you about to see one of the many futures our planet might reach, a future in which far and near are no different? A future in which pasts and futures are just travel directions for our descendants to choose from? Time travel has been a human fantasy for ages, but you've never heard of anyone actually making the trip. Stephen Hawking once held a party for time travelers at midday on June 28, 2009. To make sure only time travelers showed up, he didn't send the invitations until after the party. No one came. So what is this new journey of yours supposed to tell you, an insignificant organism lost in the immensity of space and time? The glass corridor you've been walking through eventually curves into the lobby of a huge airport, or maybe we should call it a time port. Hundreds of people are queuing to get through what seems to be some form of customs. The hall is very bright. Light pours in from gigantic window panels looking out at skyscrapers rising from the sea. As you join one of the many lines, blending with the other passengers, you suddenly fear that what you are experiencing now is not a dream, but real, that what you dreamt was being back home. Understandably, this makes you anxious. If this is real, then what happened to your past? If you've really traveled 400 years since takeoff, is the past you left behind still somewhere out there? Could you, if you wished, travel back to live that past life through? Or is it gone forever? And the dear friends who sent you home from the island, are they all long dead? It dawns on you that this must be the case. That you squeezed past their time towards the now. The interplay of time and space may be tricky to grasp, but you find it hard to imagine that several lives could be lived by the same person simultaneously, in the same universe, while he or she was aware of them all, even though fields seem to allow exactly that in the case of particles which no one is looking at. What is possible for single particles appears not to be possible for collections of billions and billions of them, such as the human body. As your mind reflects on that fact with a certain sadness, you become almost physically aware of the unbridgeable gap that now separates you from all the people you loved, and sorrow grips your heart. But there is a certain solace in what you have seen so far. Your loved ones' past lives have become a succession of images moving through space and time. All the light and other massless particles that once bounced off their bodies, or interacted with them in even the smallest way, created a memory of their existence, an image, a shell that spreads at the speed of light from the Earth towards faraway unknowns, small ripples on invisible but ubiquitous fields. And since you've traveled 400 years into the future, the visible memory of their lives presently washes over planets and stars that lie 400 light-years away from Earth, and their image will keep moving away, spreading further, maybe falling here and there in some light-gathering device aliens might be using, for as long as our universe will be. And what about the matter they were made of? What about those atoms that were born billions of years ago in the core of long-gone stars, before coming together to form the bodies of your friends and loved ones? All their trillions of particles are now scattered throughout the world. You may even be near one right now. All particles are but one anyway. Perhaps we are not that small in the scheme of things after all, you think on reflection. Our image is here and will forever stay, and there is comfort in knowing that the memory of our lives will always be there, traveling among the stars. Time, space, and fields make us all belong to an extraordinarily large reality. Spreading your arms to feel the fields you are made of, lifting your hands high in the air to see them climb the invisible slope the Earth creates in its surrounding space-time, you begin to understand how interconnected all pasts and presents and futures may in fact be. Is everything all right, sir? A uniformed woman suddenly asks. Snapping out of your reverie, rather embarrassed not to have seen the woman approach, you barely manage to mumble that yes, you are fine, but some things in life never change. Even in the year 2415, everyone immediately feels like they're guilty of something when faced by a trained customs officer. When are you arriving from, sir? Inquires the lady. Early 21st century, you reply, trying to sound as familiar with this kind of travel as is possible. Please follow me, sir, she says, her tone making it clear that this order should not be mistaken for a request. As pretty much all the other arriving passengers nearby cast a reproachful glance at you for being in trouble, you step out of the line and follow the officer through the hall. Is something wrong? You ask, as a door slides open in front of the customs officer. Please step inside, sir, is the only reply you get. Inside, another officer is seated behind a large desk. Behind him, above his head, a large sign reads, Time Travel Distress Psychological Ward. Any offense against our staff will lead to immediate prosecution. Obviously displeased to have yet another patient to deal with, the officer impatiently waves for you to sit down in front of him. Looking around in despair, you begin to break out into a sweat. The room is empty. There's just the desk, the unfriendly officer, the sign and a now familiar yellow tube protruding from the side of the desk. All your worries are immediately blown away as you recognize your particle-throwing companion. Is this another simulation? You wonder. If so, it has certainly made you feel a little better about your place in the universe, and reflective about the nature of life and death. The quest to understand reality is a personal one, when all is said and done, and neither the supercomputer nor I should impose our views upon you. It's your right to have ideas of your own. Still, I should here warn you that, so far, you've just skimmed over the two theories that scientists use to describe our universe, quantum field theory and Einstein's theory of gravity. 46 They certainly both look coherent and elegant, but you should know that there are problems with many of the concepts they involve. In fact, to be completely honest with you, no one really understands the universe yet. Even the reality that is around you, right now, or on your sofa, or on a tropical beach, is clouded in mystery. But one thing is for sure. All the mysteries that count, whether they be around you or within you, or far away beyond the Big Bang, eventually lead to the unification of the quantum fields with a quantum theory of gravity. And while it is true to say that such a theory of everything is not known, at least one of the properties of quantum gravity has been found. A clue, if you like. A clue that gives a tantalizing hint of what lies beyond the Planck wall. That's the good news. The bad news is that there's only one known window that opens onto this clue, a window that suggests it might one day be possible to travel, if only in our minds, beyond the origin of spacetime. And that is why the robot has come to collect you at the time port. As the room you're in disappears to reveal yet again the dark landscape of deep space, you begin to ask about your destination but are cut off mid-sentence. "I'm taking you to a black hole," announces the machine. As you travel to one right at the start of your cosmic adventures, you are perhaps wondering what you missed on that first visit. The answer, for once, is rather simple. You didn't get close enough. Part 6. Unexpected Mysteries. 1. The Universe. When you think about it, there is something peculiar about the universe we belong to. Its name, universe, comes from uni and verse, so its name basically means turned into one, highlighting, from the start, a very particular problem it raises. Any experiment made within our universe can be repeated many times over. Want to check Newton's law of gravitation on Earth? Shoot an arrow. Not sure you got it right? Shoot another one. Again and again. With patience you will see that, from the knowledge of its initial position, angle and velocity, you can predict where the arrow will land. That is what ballistics is all about. And it works. Bows and arrows would have been abandoned long ago otherwise, and England would be French. So, with a law and an initial condition, you can, it has been proved, predict where an arrow lands and defend a whole country. For the universe as a whole, it is a bit more difficult. Even if you had a law that explained everything, that applied everywhere, how would you make it work? How would you use it to predict how the universe we live in today became the way it is? You'd need an initial condition for that, which you don't have. But you could try to outsmart nature. Starting today, running time backwards, you could maybe reach an initial event that occurred a long time ago. That is what scientists have done. That is what you did back in part 5. And they and you reached the Planck wall. Which is a pretty good start, since it corresponds to when space and time became what they today are. But that doesn't remove the frustrating fact that, unlike with your experiment with the arrows, you only have one universe to play with. You can't have a go at creating another one with different initial conditions and check what comes out of it. Not in the lab, anyway. But what if ours isn't the only universe? What if we were part of yet another type of multiverse, different from the one you were introduced to at the end of part 2? Could our reality be only one of a myriad of possible realities, all having different beginnings, maybe even different laws, and hence very different presents? The idea of such a multiverse is a question you will soon have to face, because it forms part of the answer modern theoretical physics has come up with to the mysteries you will probe throughout this part. Indeed, this section of the book is going to be a bit different from the previous ones. In parts 1 and 2, you traveled through the very big. You learned about gravity. In part 3 you saw what our reality looks like when traveling very fast, and then, in part 4, you entered the realm of the very small. In short, until now, you've probed the relativity of time and space, and quantum physics. But nowhere, until now, did you mix gravity and quantum ideas. This is what you will aim to do here. For this, you will have to exercise your mind a little, just as you would exercise your body by stretching it. Mixing gravity and quantum physics means mixing the very big and the very small. So, to ready yourself, your mind will have to learn how to jump from the very small to the very big, and back to the very small, again and again. In doing so, you will see what goes wrong with the theories you've seen so far. When that is done, you will journey with your robot guide to a place where gravity and quantum effects are both at work. For now, however, let's have a look at the mysteries of modern science together, just you and me. One can argue that there are 3 kinds of mysteries in physics. The first ones are inherent to the theories themselves, they are theoretical. The second ones are rooted in observations and experiments. These are the ones that usually, but not always, drive research. The third type of mystery arises when no one understands anything anymore. Black holes and pre-spacetime physics belong to all three types. They are both bridges and obstacles that lie between us and the holy grail of modern research, a theory that unifies the quantum world and the dynamical aspects of spacetime that Einstein figured out. That's why they're exciting. And that's why the robot is keen to take you near to a black hole. But why a black hole? Why not to the origins of the universe itself? Because in the case of both the black hole and the birth of the universe, a huge amount of energy is confined within a pretty small volume. In both cases, the very big shrinks into the very small, and in both cases, neither gravity nor quantum effects can be ignored. In that sense, black holes and our universe's origin look very similar. One can't look at the universe from the outside though, of course. Experimentally, even if we had a law that governed the behavior of everything there is, visible or not, we couldn't check whether different initial setups give different evolutionary models for our universe as a whole. We can't create big bangs in the lab, and we don't see new universes appear out there in the night sky, for us to analyze them. Which is why black holes are useful. For one, there are lots of them. Pick pretty much any galaxy in the universe, and there is probably a supermassive black hole at its center. There may also be many more, smaller ones, with masses a few times that of our star, distributed everywhere. As of 2015, the largest black hole ever detected is 23 billion times the mass of the Sun. It lies some 12 billion light-years away, in what was a very young galaxy at the time it emitted the light we catch today. At the other end of the scale, theoretically, the smallest black holes can measure anything down to the so-called Planck scale limit, which corresponds to an environment where gravitational and quantum effects both have to be taken into account. In numbers, the Planck length corresponds to 16 millionths of a billionth of a billionth of a billionth of a millimeter. So tiny that for all practical purposes, black holes can be of any size at all. Both black holes and the very early universe share some important common features. They both involve a limit beyond which gravity cannot be used without incorporating quantum effects. That limit is the Planck wall, the wall you saw when traveling back in time beyond the Big Bang at the end of last part. Around the universe's birth, this wall was everywhere. For black holes. However, it is normally hidden from view, behind a gate that only opens one way, a horizon. You will cross one at the end of this part. That trip will be the key that will lead you to part 7, where you will embark on your ultimate journey, a voyage through the universe as seen by the most popular of modern theories, a vision of everything that endeavors to unify space, time and quantum fields. But these theories, called string theories, are so crazy, entailing both multiple and parallel universes, extra dimensions and all, that you could very well start believing that scientists have rather lost their marbles. If it were not for the mysteries they solve, that is. After all you've been through to reach this page, you may find it amusing to learn that, far from having discovered nearly everything, 20th century physics has left us with a picture of our universe that is mostly filled with deep and dark unknowns. This should not, however, come as a disappointment. These unknowns are the windows we have on the science of tomorrow. And, between you and me, seeing how much mankind's understanding about pretty much everything has evolved in less than a century, seeing the baffling ideas that are today sprouting in the minds of theoretical physicists, there is little doubt that more revolutions of thought are still to come. Some may even be ripe or ready to bloom, just lacking the right experiment, ready to mold our perceptions with the promise of a strange, magical new reality. So, here is what is going to happen to you now. First, you will have another look at the quantum fields that fill our universe, and you will see that, despite what I've told you so far, they make absolutely no sense. Then you'll have yet another look at all the particles these fields give rise to in the context of quantum gravity, and you'll see that they make no sense whatsoever either. Then you'll meet a cat, which is both dead and alive, and you will, if you follow it all, not understand anything anymore. Strengthened by these successes, you'll hear about parallel universes splitting off from ours like branches on a tree. Once convinced that the quantum world is utterly beyond what our common sense would have us believe reality is like, you will move on to more familiar territory. Aiming, eventually, to bridge the gap that separates the very tiny and the very big, you'll turn to the big picture again, for a fresh look at Einstein's theory, at our universe's galaxies, at its expansion, hoping to find it all reassuringly well-defined. Funnily enough, you won't. You'll see for yourself that most of what our universe contains is not only invisible to our telescopes, but also unknown. The universe on a large scale is filled with mysteries wherever you look, just as it is on a very small scale. Reluctantly or not, you'll then have to digest the fact that, however powerful it has been and will forever remain, Einstein's theory of a curved space-time is incomplete, that it even predicts its own breakdown and therefore cannot be a theory of everything. There are places within our universe where it cannot be used. This means that a bigger theory needs to be found, if one ever intends to explain everything. Where does it break down? You've probably guessed, within black holes and before the Big Bang, somewhere on the way to the Planck wall. So far, you have been traveling through the best theories mankind has ever built to describe the world that surrounds us. In practice, it means you now know as much about our universe as a good graduate student from any of the best universities on Earth. Not in technical terms, obviously, but certainly in terms of ideas. It should already be enough for you to shine at any dinner party. Now it is time for you to go further and see what doesn't work. And then you'll not only shine, but also be able to make your friends scratch their heads in disbelief. 2 quantum infinities. Do you remember seeing what the outer space vacuum really looks like? What had until then seemed to be but emptiness turned into a wilderness of fluctuating fields. Fluctuations became particles that popped out of the field's vacua, everywhere. In the quantum world, when something is possible, it happens. So, forget about your normal everyday size and about gravity for a moment and picture your mini-self immersed within quantum fields, in the world of the very small, sitting on a mini-chair. You are like a referee, watching 2 electrons interact with each other, just as you might watch a game of tennis, the electrons being the players, the balls the virtual photons that dance between them. There is an electron somewhere to your right, and another to your left. Being exactly identical, they both carry the same electric charge. Like magnets, they should repel each other. This should be fun to watch. The electrons are far away for now, propagating within the electromagnetic field they were born from. They move closer to each other, they are about to hit each other, but they don't. They interact. They play. Virtual photons pop out of the electromagnetic field, deflecting the electrons, scattering them. Then, as quickly as it began, the game is over. The electrons and the virtual photons are gone. You wait for the next game. Another pair of electrons is on its way. You decide to focus on the virtual photons this time, rather than the electrons. You sharpen the focus of your mini-eyes. The electrons are moving. They are getting closer and closer and pop. Virtual photons appear. Not to miss anything, you slow down the passage of time. The electrons are about to be deflected. The virtual photons are there all right. But something is happening. One of the virtual photons that appeared in between the 2 electron tennis players spontaneously underwent some strange metamorphosis. It became a particle-antiparticle pair, an electron and a positron. You cast a quick glance towards the electrons, curious as to whether they might be affected by having lost their virtual pearl of light, but they don't seem to mind at all, so you look back at the pair just created, and it is not a pair anymore, but 2.5. You close your mini eyes and rub them. What kind of game is this? You open your eyes again. There are suddenly thousands of pairs of particles and antiparticles between the two electrons. You blink. There are hundreds of millions of them. And now thousands of billions. You blink again and they're all gone. You check the electrons. They've scattered. Just like the previous players. Amazing. What you've witnessed is one consequence of the quantum rules that apply to the very small. If something is possible, it happens. And it is very possible for virtual photons, dipping into the moving electron's energy, to turn into virtual pairs of antiparticles, which in turn can become further pairs of antiparticles, which in turn can become further pairs, or annihilate back into light, which in turn can. You get the idea. Even when just two tiny electrons interact, the possibilities of virtual pairs appearing during the interaction are infinite. And so an infinite number of virtual pairs is involved. Pondering this, still sitting happily atop your mini-referee's chair, you wait for the next game in order to witness the fireworks again, but there aren't any more players. No electron is coming your way. Still, now that you know what to look for, you see virtual pairs of antiparticles appear all the same, albeit at a slower pace. They look like tennis balls and anti-balls popping out of nowhere, with no players around. These pair creations are the quantum fluctuations of the vacuum. They are present all the time, but when there is some available energy for them to tap into, like the kinetic energy of some incoming electrons, they get much more excited. An electron-positron pair spontaneously appears in front of you, and the pair annihilates into a photon, which spontaneously turns into another pair, a quark-antiquark pair, and now one of the antiquarks emits a gluon, which in turn. Even in the vacuum, when there seems to be nothing around, to build a correct picture of our world, all the infinite possibilities of antiparticle creation have to be taken into account, everywhere, all the time. A mess. A mess with a rather catastrophic consequence. The possibilities are so important and numerous that there should be an infinite amount of energy at each and every point of our universe. Even where there is nothing else, in the vacuum. Rather obviously, this is not the case, or our universe would collapse everywhere, right now, because of the extraordinary gravitational impact this would have on spacetime. So there's something wrong with this picture. To make this rather cumbersome problem easier, quantum field theorists came up with a pretty cunning trick. They purely and simply decided to forget about gravity, to entirely remove it from the game. And, while they were at it, they got rid of the infinities too. They turned them off and made calculations with what was left, and abracadabra. It worked. Dutch theoretical physicist Gerard T. Hooft, to name but one of the amazing and brilliant physicists who fathered such mathematical surgery, jointly received, with his PhD supervisor Martinus Veltman, the 1999 Nobel Prize in Physics for this. Thanks to them, and despite the mathematical hocus-pocus to account for the infinities, quantum field theory arguably became, through its predictive power, the most successful scientific theory of all time. Getting rid of the infinities led to predictions about particles that hadn't even been seen before, predictions that were accurate as far as their mass or charge was concerned, up to 1 part in more than 100 billion. Were a randomly chosen person to be that precise, he or she would be able to guess if a drop of beer was missing from 1,000,000 pints served in a pub. Riots would no doubt occur on a daily basis if we had such a capacity. Quantum field theories are astonishingly precise in their predictive power, but this trick leaves us all frustrated for reasons that even 1,000,000 beers can't help wash away. Why do these infinities occur? Could it just be because we do not know what is happening in regions of our universe that are even smaller than the ones these theories are probing? Perhaps. That is what one extraordinary American physicist thought, anyway. His name was Kenneth Geddes Wilson, and instead of trying to explain infinitely smaller realms to reach a conclusion about particles, he thought that such dizzying scales might actually be the problem, that one should not necessarily have to consider ever smaller scales in order to be able to talk about particles. Just as one does not need to know about atoms to compare apples on a market stand, Wilson argued and proved that what is not known could be gauged and codified and forgotten about. And it worked. Indeed, he received the 1982 Nobel Prize in Physics for it. Wilson didn't solve the problem of what happens in the infinitely small, though, he just got rid of it. Introducing a cutoff, coarse-graining what wasn't known, the infinities that had marred the field before did not occur anymore. The process of removing infinities has a name. It is called renormalization. As I said above, it is brilliantly efficient for making calculations. But to ever have a hope of understanding everything, one cannot just bypass the unknown. One needs to dive into it. Especially so because with gravity, these renormalization procedures do not work. Quantum field theories are about what the universe contains. They are very accurate, astonishingly accurate really, but only when they leave the background spacetime alone, fixed, with gravity having no effect on anything whatsoever. Not a very realistic world. We need to find a way to bring gravity back in. We need to turn gravity into a quantum field. So how can that be done? Quantum field theories assert that as soon as there are fields around, these fields can create small packets of energy, or small packets of matter, which are called quanta. 47 The basic quanta of the electromagnetic field are the least energetic states of its elementary particles, the photons and the electrons. Similarly, the basic quanta of the strong nuclear force field give the quarks and the gluons, whereas the basic quanta of the gravitational field, considered as a hypothetical quantum field, are what we earlier called the gravitons. You heard about these before, in Part 5, but we dismissed them back then. Why have they reappeared here? Because we'd like to see what could be wrong with them. So let's think of gravity as arising from a quantum field like all the other fields you've seen so far. The gravitons then are its force carriers. And when they calculate, on paper, how these gravitons would affect their surroundings, theoreticians find that they would be just like the curves of spacetime. On paper, they are gravity. A very promising start. But it so happens that when they think further, scientists realize that those very quanta of the gravitational field, those gravitons, also make the straightforward idea of gravity fail completely. Which is not a very good thing. Why is it so? First, gravitons have no reason not to interact with one another. Were they to exist, then they should, by all means, be as subjected to gravity as everything else, and hence to themselves. And second, being elementary particles of a quantum field, they should also be able to appear everywhere out of their field's vacuum, leading to infinities just like the ones that T. Hooft and Veltman cured. This time, however, the gravitational quantum infinities cannot be removed by any renormalization procedure. Here, T. Hooft and Veltman's machinery fails utterly, and Wilson's approach doesn't apply at all, since it ignores the very distances at which the gravitons act. All in all, this means that really problematic infinities arise when trying to turn gravity into a quantum field in a standard way, and one obviously cannot turn a blind eye to gravity to get rid of them, because gravitons are gravity. If gravity was a quantum field as we just mentioned, if gravitons were a correct description of how gravity works in nature, spacetime should react to these infinities and collapse pretty much everywhere. Which it doesn't. Or we wouldn't be here to talk about it. Funnily enough, despite all this, and you may believe they are lunatics, many scientists believe that gravitons do exist, at least as part of the bigger theory that everybody is looking for. Now, while we're at it, let's go further still, so that you see, right from the start, several reasons why Einstein's theory of general relativity and quantum field theory are at odds. Gravity has to do with spacetime. With space and time, that is. Intertwined. In a quantum field theory, the elementary particles that pop out of the vacuum are made of the field itself. In the case of a quantum field theory of gravity, the elementary particles should therefore also be made of their field. But that field is spacetime. So the particles should be made of space and time themselves. This means that there should be fundamental packets of spacetime around, everywhere, and, incidentally, that neither space nor time should be continuous. Worse, these packets of spacetime should be able to behave both as waves and as particles. And be subjected to quantum tunneling, to quantum jumps. Good luck trying to picture that in your mind. In fact, if you are a normal human being, just trying to think about it should make your brain melt. As far as nature is concerned, however, it should not be a problem. A real problem, though, is that even if we forget about the troublesome infinities, all the other quantum field theories that are so powerful in describing all the particles we are made of only work as long as there are no such packets of spacetime around. In other words, it means that general relativity theory and quantum field theory do not use the same notions of space and time. And that is a problem. A very big problem. With no obvious solution. And one is therefore left with a curious feeling of being stuck in the middle. Mankind has uncovered two extremely efficient theories, one that describes our universe's structure, and one that describes everything our universe contains. And these two theories won't talk to each other. For a very long time, even the physicists working on each of these two fields followed suit and did not talk to each other either. U.S. theoretical physicist Richard Feynman, Nobel Prize laureate for his work on quantum field theory and one of the most brilliant scientists of all time, wrote a classic letter to his wife accounting for this. "I am not getting anything out of the meeting," he stated, in 1962, after attending a gravity conference. "I am learning nothing. Because there are no experiments, this field is not an active one, so few of the best men are doing work in it. The result is that there are hosts of dopes here and it is not good for my blood pressure. Remind me not to come to any more gravity conferences." Yet, thanks to new technologies and the work of theoretical physicists such as Stephen Hawking, scientists soon found out they could not turn a blind eye to what they did not know, and ideas from both sides began to spill over to the other, giving birth to the crazy ideas you will travel through in Part 7, to which I'll now introduce you. 3 to be, and not to be, rather. Do you remember those quantum particles the robot played with in the white room with the metal post? Down there, in the world of the very small, particles really do take all possible and impossible paths to get from one place to another, from one time to another, as long as no one looks. So why don't all the quantum aspects of all the particles that make up your body turn you into a quantum you? Wouldn't that be cool? All the different life paths you could possibly imagine would simultaneously occur. You'd be very rich and very poor and married and single and happy and sad and win a Nobel Prize and be completely dumb and be here and there and live now and then. You'd live all the lives you could dream of, really, and all the ones you wouldn't want to. But this doesn't seem to be happening. You are made of quantum stuff, aren't you? So it should happen. But it doesn't. Why? Well, as amazing as it may sound, no one knows. In fact, it is linked to one of the greatest mysteries of the quantum world. Why do we not see quantum effects everywhere around us? Being made out of quantum particles, expressions of quantum fields, like everything else, why do we experience the world the way we do and not the way particles do at a tiny, subatomic level? One could argue that the world is the way it is, that physics is not about questioning its rules but about trying to decipher them. There is, however, a slight problem with such a humble statement. The laws of the quantum world are so very different from the reality we perceive on a daily basis that there should be some sort of transition between the quantum world and the classical one, as the one we experience, the one we are used to, is called. Were the particles that make up our bodies, or that are found in the air or in outer space, to behave like decent tennis balls or baseballs, then everything would be fine. We would understand everything from the tiniest elements to the largest ones. But they don't behave like that. You've seen they don't many times throughout your journeys in the world of the very small. When trying to catch the electron that swirls around a hydrogen atom, for instance, do you remember how hard it was for you to know both where it was and how fast it was moving? Well, let's have another look at this fact now. Picture yourself in your mini-you state. You are smaller than an atom. A particle is on its way towards you. You know nothing about it, neither its size, nor where it is, nor how fast it is approaching. You just know it obeys the rules of the quantum world. You take out a mini torch from a mini bag you brought along and get ready to switch it on, expecting its light to bounce off the particle, wherever it is, and travel back to you, thereby telling you its position. But you can't use just any light to do so. You need to use the right light. Remember that light can be thought of as a wave? Well, the right light here means that the separation between two consecutive wave crests has to be roughly the size of your target or smaller. Use too large a wavelength, and the light it corresponds to won't notice the particle at all. It will shoot through it, just as radio waves travel through the walls of your house without even noticing them. With the right wavelength, however, you'll get a bounce back and you will be able to tell your particle's position with the accuracy of the wavelength used. Simultaneously, you'll be able to check what the particle's velocity is and you'll know everything you want to know about it. Easy. You adjust the knob of your state-of-the-art mini torch to get a very energetic pulse. Focused, you shoot and bam! You hit something. A particle. There. Ahead of you. Light bounced on it and traveled back to you. The time it took to travel there and back tells you exactly where the particle was at impact, and the particle therefore cannot be everywhere anymore. Once detected, the particle loses its quantum wave attributes. From all the possible positions it held simultaneously a fraction of a second before, one was picked up by the very act of using your torch as a probe. Just like when the robot threw that particle in the white room, the particle went everywhere until it got detected by a detector. This irreversible process is called a quantum wave collapse. After the collapse takes place, you know where the particle is, up to the accuracy of a wavelength. Now you want to know how fast it was moving at the point of impact. But that is not going to be so easy. In fact, you won't be able to answer that question exactly. Ever. Remember, the shorter the wavelength, the more energetic the light it corresponds to. So the more precise the position you get, the more energetic the light you had to use for your torch, the harder you hit your particle and the less you therefore know about its subsequent velocity. In the world we are used to, this is a trivial statement. Try, in the dark, to pinpoint the position of a moving object by firing something at it. The impact will affect what you wanted to probe. If what you fired bounces back to you, you'll know where the object was at impact, but if you fire once more to know where it went, you'll see that its velocity changed because of your first shot. Trivial indeed. In the quantum world, however, that is not just a trivial uncertainty. It is a deep property of nature. It says that you fundamentally cannot know both where a particle is and how fast it is moving. This rule is called the Heisenberg uncertainty principle after German theoretical physicist Werner Heisenberg, who discovered it. Heisenberg is one of the founding fathers of the quantum theory of the atomic world. He received the 1932 Nobel Prize in Physics for it. He knew what he was talking about. But, like everyone else ever since, he did not understand it. It is beyond our intuition, it is contrary to common sense. The uncertainty principle immediately makes the quantum world very different from our everyday, classical world. Right now, with respect to your body, you know where the book you are reading is and how fast it is moving. You hence know its position and velocity with a pretty good level of accuracy. Still, there is an uncertainty about its position and velocity too, an uncertainty too small for you to notice, and therefore an uncertainty that doesn't really matter. In the very small, however, in your mini-you state, you wouldn't be able to hold a book in your hands, or even a torch. Were you to precisely know where a mini copy of this book was, the uncertainty about its velocity would be huge because you'd be firing many particles at it just to know where it was, and you would never be able to look at it. Alternatively, were you to know precisely how fast it was moving, you wouldn't be able, by any means, to know where it was, making it tricky to read. In the very small